welcome to you all to this course of Thermal Engineering 2. In today's session, we are going to discuss about solving for enthalpies in the Rankine cycle. The topics to be covered in this session include process in the Rankine cycle, solving for enthalpies in all states of Rankine cycle, followed by thermal efficiency. Coming to the process in Rankine cycle, if we represent all the process of Rankine cycle in a HS diagram, it would look like this. So all the process operate between two pressure limits. P1 bar is the maximum pressure and P2 bar is the minimum pressure. So four process, that is for process in the pump, 1 to 2 is the process in the pump, 2 to 3 is the constant pressure process inside the boiler, 2 to 5 and 5 to 6 is the constant isentropic process in the turbine, 6 to 1 is the constant pressure process in the condenser. So all these process happens between two pressure limits P1 bar and P2 bar. So in this video, we are going to learn how to locate enthalpies or how to know the enthalpies at each state. That means at state 1, state 2, state 3, state 4, state 5 and state 6. We are going to know how to find out the enthalpies at these 6 states in order to calculate the thermal efficiency of Rankine cycle. So here if we observe, this is called the saturated liquid line. So all the points on the saturated liquid line are represented with suffix F. That means HF is the indication, H suffix F is the indication for the points on the saturated liquid line. And all the points on the saturated vapor line are represented with suffix G. That means Hg is the indication for saturated vapor region. And in between these two, that means in the enthalpy that lies in between these two, that means saturated liquid line and saturated vapor line is denoted with HFG. That means if we consider, let us consider a point 1, since point 1 is in the saturated liquid line, it is denoted with HF. So HF1 is the indication of enthalpy at state 1. That means if we, and 4 is a point on saturated vapor region and Hg is the indication of saturated vapor region. And the difference between these two gives this region. So the amount of latent heat that is removed is the difference between the saturated liquid vapor region and the saturated liquid region. That means HFG is the latent heat that is removed, which is equal to this Hg minus this HF. So HFG can also be written as Hg minus HF. That means if we know the values of Hg and HF, we can calculate the value of HFG. So let us now know how to calculate the enthalpies at each state separately. So coming to state 1, here if we observe, we are going to find out the enthalpy at state 1, that is H1. Since H1 is a point on the saturated liquid region, it should be denoted with HF1. F denotes saturated liquid condition. So H1 can be represented as HF1. So HF1 can be directly found out from the steam tables and H1 lies on the pressure P2 bar line. So we have to go to the saturated steam tables and at a particular P2 bar pressure, for example it is atmospheric pressure or 1.013 bar, at this particular pressure the value of HF value, that means 419 kilojoule per kg is the value of enthalpy at state 1. That means here the values of enthalpies are given in kilojoule per kg since it is a specific enthalpy. Enthalpy per unit mass, capital H by M gives rise to small h, which is called as specific enthalpy. In steam tables, we will obtain all the values of enthalpies in specific quantities. So the enthalpy at state 1 can be found out from the steam tables at pressure P2 bar, since one lies on pressure P2 bar, and the corresponding value of HF 419 is the answer. And coming to state 2, state 2 neither locates on saturated liquid line nor it locates on the saturated vapor line. So we have to find out separate. So what we are doing here is, since 1 to 2 is the process or the work input that is given to the pump, the work given to the pump is given according to PdV or VdP is non-flow work is, flow work is Vf into P into dV. dP means change in pressure, P1 minus P2 into specific volume. Specific volume at state 2. So at pressure P2 bar. So this pressure line. So here the work done in the pump can also be written as the change in enthalpies between these two states. That means H2 minus H1. So equating these two equations, so work done can be written in two ways. First one is in the form of VdP, and second one is in the form of enthalpies. If we equate these two terms, specific volume can be directly found out from the steam tables at a particular pressure, and P1 and P2 are these two pressures. HF1 is already found out in the previous session, so we can calculate the value of HF2 by equating these two terms. So coming to state 3, so if we observe, state 3 is a point on saturated liquid line. So state 3 should be denoted with a suffix F. So H3 can be directly obtained as HF3. That means by seeing steam tables at this particular pressure. So since 3 is a point on P1 bar pressure line, so we can obtain the value by seeing the steam tables at a pressure P1 and corresponding to saturated liquid region. The enthalpy at this state 3, particular state 3, HF3 can be obtained. It is just similar to that of state 1. Next, coming to state 4, if we observe, state 4 is a point on saturated vapor line. So in saturated vapor line, the enthalpy can be represented with a suffix G. So H4 can be represented with a suffix G value. That means Hg4. So this value, this particular enthalpy value can be found out from the steam tables by seeing at pressure P1 bar and corresponding to saturated vapor region, Hg value. And the enthalpy at state 4 can be obtained. And coming to state 5 here, so state 5 is the superheated region. So this is a saturated liquid line, this is a saturated vapor line, and this is the superheated region. In superheated region, we need two values. First one is the pressure, the particular pressure in which the superheating is taking place, and up to which temperature we have to know. So in order to find the enthalpy at state 5, we need two values, pressure and temperature. So we have to go to that particular pressure value. So here, if for example, if the pressure is 1.5 bar, this P1 bar is 1.5 bar. So for 1.5 bar at a particular superheated temperature of 320 degrees centigrade, the enthalpy value is given as 3113.5 kilojoule per kg is the value of H5. So once again I am repeating. So in case of superheated region, if we want to know the enthalpy values, we need two values. First one is temperature and second one is pressure. So we have to go to that particular pressure value, that means P1 bar value, say if it is 1.5 bar, and that particular temperature value, that is 320 degrees centigrade. So under 320 degrees centigrade, the corresponding H value is 3113.5 kilojoule per kg Kelvin is the value of H5. And next, coming to state 6. Since state 6 is neither in the saturated liquid region or in the saturated vapor line, or it is nor it is a superheated condition, it lies in between the saturated liquid line and saturated vapor line. That means it is in wet condition. Wet condition means it is a region where there is both liquid and vapor. So that means when it travels from this point to this point, saturated line, liquid line to saturated vapor line, liquid is converting to vapor. That means here X is equal to 0, and saturated liquid line there is no dryness fraction. So here the dryness is 0. As we go on reaching the saturated vapor line, the dryness value increases. That means X value increases. Here X represents dryness fraction. Dryness fraction is the amount of moisture content or amount of removed. So amount of vapor present in liquid plus vapor mixture is the dryness fraction. So H6 can be written as HF6. So up to this, plus we have to add this quantity. This quantity can be represented as HFG multiplied with dryness fraction X6. So in order to find out H6, we need to calculate three terms. First one is HF6, second one is X6, and third one is HFG6. So here HF6 and HFG6 can be directly found out at a pressure P2 bar. So since 6 point lies on pressure P2 bar, we can find out HF6 directly. But X6 should be found out. X6 is calculated by equating the entropies at these two states. Since this is a constant entropy line, so if the entropy at state 5 is equal to entropy at state 6, so S5 is equal to S6. So the value of S5 can be directly found out from superheated steam tables here. So at a particular pressure here, besides enthalpy value, we can see entropy value also. This is equal to S5 at a particular pressure. So entropy can be found out directly from the superheated steam table, since 5 is a point on the superheated steam region. And S6 and SF6 and SFG6 can be found out from the steam tables at pressure P2 bar, where we see earlier. So if we substitute both of these two and we know the SF5 value, X6 can be found out easily. Once we know the value of X6, if we substitute this X6 value in H6, we can find out H6 value easily. So after finding out all the enthalpies values at all the states, the final one is to find out the thermal efficiency. So thermal efficiency is given by net work output by heat input. So net work can be written as turbine work minus pump work by heat input. So turbine work means H5 minus H6 and pump work is H2 minus H1. And the amount of heat input is H5 minus H2. So since we know all the enthalpies at all states, we can find out thermal efficiency easily. So in order to find out thermal efficiencies, the first step is we have to know the values of enthalpies at every state of the complete cycle. That means if we say that it is a superheated region, so if the boiler pressure ends here only, we can see that from the saturated liquid vapor region. Like that, we have to find out all the enthalpies, and if we found all the enthalpies, the thermal efficiency can be found out easily. Thank you, and in the next session, we will solve one problem.